Hi guys, so I'm going to give you a quick lecture on 7.5 motion graphs. So these are the collection of graphs of displacement time, and velocity time graphs. Excuse me. Now, these are really useful to show certain types of motion, and they are very much related to each other. So I'll just show you what a displacement time graph might look like. Now, one of the first things to realise is that both displacement and velocity are both vectors, which means that the y-axis can go both positive and negative. So if we look at a simple displacement time graph, right? So I'll just put S on here for displacement and T along here. So say I started walking at a constant velocity, and then I was stationary, and then I turned round and went back the opposite way, and then I went back through my starting point, and then went back in the other direction, was stationary for a bit, and then walked back to my starting point. This is what the displacement time graph might look like for that. So we've got a couple of areas here that I want to look at. We've got area number 1, area number 2, area number 3, and this is also area number 3 here as well, area number 4 and area number 5. So, what's happening in area number 1? Well, we are covering, this is the way that I do it, I say what's happening. So, we are covering equal displacement in equal time. So what's happening there? If we're doing equal displacement in equal time, well, that's a velocity. If you usually 1 meter per second or 2 meters per second for a number of seconds, we are doing a constant velocity. Now, section 2, we can look and see what's happening. Well, section 2 on the graph, what's happening there is staying the same displacement. Away from the start. So that means we're stationary. It can also mean, if you're clever, that you're circling round. But in this case, we're stationary. Now 3. So we've kind of turned around on the spot, and we're going negative displacement now. So we're going backwards. So we're covering negative displacement in equal time. So that would be a constant negative velocity. Well, part number 4 is just the same as part number 2. And part number 5 is just the same as part number 1. To get us back to the start. Now, see if I can do something clever. Oh, no, that wasn't as clever as what I thought. This is just going to be in one take, so you might have to bear with me here. Try once more. Going to copy this graph down here, so we've got, there you go, done it. Learn how to use some new technology today. So that was our original displacement graph from above, and now I'm going to draw what the equivalent velocity time graph would look like with all those different sections. So I'm just going to make sure I line it up properly, so that's where we went through the middle. So we started off at section 1 at constant positive velocity. So that's going to be like this. And then I said we immediately stopped. And then we immediately stopped. Part 2. And then we had a negative velocity for a while. And then we stopped. And then we had a positive velocity again. So let me write on the different sections. This is section 1. This is section 2. This is section 3. This is section 4. And this is section 5. Now, what's wrong with the scenario that the very simple scenario I've given is that I said we stopped instantaneously. Basically, I said we stopped instantaneously. I.e. without deceleration. But in reality, we do have acceleration and deceleration. So let me just show you what they look like on a displacement time graph and a velocity time graph. So this will be quite simple, this one. So displacement time graph, if we have a curve like that, that is acceleration. Because you are covering an increasing amount of displacement with equal time. So here, this is acceleration. Now, what does it look like on a velocity time graph? Well, that just looks like a straight line. Because your velocity is increasing at equal rate in equal time. That is called an acceleration. So again, that is the same thing. But why is that? What is the relationship between S and V? Well, you know from maths that displacement, velocity is the rate of change of displacement with time. So it would make sense that the gradient of the displacement time graph was a velocity. And you also, taking it one step further, you know acceleration is equal to the rate of change of velocity with respect to time. Which happens to be the second differential. So my pen is not working quite correctly. So, which is the second differential of displacement with respect to time. You don't really need to know that, but it's just useful if you think mathematically to visualise what's going on with the graphs. It's particularly helpful in year 2 when we do simple harmonic motion. Now, a particular example I just wanted to go through with you is if we just show you the power of a displacement time graph in different scenarios. Say, for example, we throw a ball up in the air. This at the top here would be its max height. And that would be fairly simple. Now, if you saw this on a distance time graph, call it D, it would look something like this, with the max distance in here, or the max height, sorry, in here. Why? Because this graph represents the distance the object has travelled in a distance time graph, whereas the displacement is how far it is from its starting point. That's why we use displacement, because it's just a little bit easier to understand. So, the last thing I'd like to talk to you about now is just what a velocity time graph for something like a bouncing ball would look like. Because sometimes these are quite difficult. So, I mean, we've seen let's look at a displacement time graph. And this may help you understand. So, I'm going to throw a bouncing ball up. I'm going to drop a bouncing ball from my hand, and it's going to bounce on the floor and then come back up. So that's what's going to happen. So my negative is going to, my downward is going to be positive. So let's look at what happens in displacement. So it's going to actually, I'm changing my mind. We're just going to look at a velocity time graph for it. I always start with velocity time graphs because they're easy to understand. If you ever have to draw these, draw a velocity time graph first. So we've still got a bouncy ball and we're going to drop it. So it's going to accelerate downwards. But then immediately, when it hits the ground, it's going to bounce and start going upwards, right? So, immediately, it's going to have some kind of velocity in the other direction, and it's going to be, so it's going to bounce off the floor here. So these are the 2 points when it hits the floor. So it's going to have a negative velocity under here when it hits the floor, because down is my negative. So we've got different parts here. So I'm going to call this part 1, this part 2, this part 3, and this line I'm going to call part 4. And I'm actually going to extend this out. And let's see what happens. And don't forget, this is dropping a bouncy ball. So, well, part one is just I've dropped it. And it then increases its velocity. In brackets negative. And 2 hits the floor. So it increases its negative velocity until it hits the floor. At which point it bounces upwards. And it would have a slightly lower positive velocity, because some of the energy would be given as heat and sound, because you can hear that. So it will bounce upwards. So say it had like, I don't know, 5 meters per second at the bottom when it hit the floor, it might only give 4.5 meters per second when it bounced up, but it would have a strong positive velocity when it bounced up. And then what would happen? Well, it's fighting against gravity, so its velocity would decrease. So it would go up in the air. It would hit the floor. It would go up in the air. Until it reached 0 velocity and then start coming back down again. So that is how we would interpret a velocity time graph like that. There's a lot of physics going on in there, and it's important that you are able to interpret these. That was a quick run through of velocity time and displacement time graphs. Any questions, please do get in contact. Thank you.